Okay, then let's continue. So we've now dealt with the probability distributions for the global maximum, which was given as a distribution function, and the number of clusters, which was which is given by a Poisson distribution. So next thing is the distribution of cluster volume. For which we also already computed or discussed the expectation and defined a random variable. So the random variable was called KU. The K is chosen because in SPM the volumes are always denoted by K. So this is why this random variable is called big KU. So the distribution of the cluster volume was introduced also by Friston et al. 1994, meaning the distribution of cluster volume as it's implemented in SPM. This is actually defined in terms of a probability density function. And I will first write down the probability density function, and then I will discuss where it's coming from. So the probability density function here is given as follows. I actually defined it on the positive real numbers. So in the paper you find some discussion that you measure the volume in voxels. That was before the Riesel stuff got into SPM. So this actually would be now in Riesels, but there the discussion is still that voxels would be discrete entities, and so it would be an integer valued thing in principle, but nevertheless it's modeled by a real valued thing. Whatever. So the thing here is that it's real valued and it's a density function which is larger or equal to 0. The values that the cluster volume can attain are denoted by small k, and these small k's get allocated at probability density. Although I have to admit that I never really checked that this is a density, and of course there's no proof in the literature that this is a density, but let's hope for the best for now. This density takes the following form: 2 beta divided by d. D is the dimensionality of the search space, so in 3D volumes usually 3. Then it's dependent on the value k to the power of 2d minus 1 times the exponential of minus beta k to the power of 2d. So that's essentially a decaying exponential here in k. The question is, of course, what is beta? Beta is given by the gamma function evaluated at d half. So gamma function just a function. Google it, then you know what the gamma function is. I think I documented that somewhere. And then it's the expected, I write it out here, the expected volume divided by the expected number of clusters, which is, of course, this thing is just the expected cluster volume. So the idea is fairly similar in terms of the stuff that we've seen previously for the Poisson distribution. So we know the expectation of this distribution, now we parameterize a probability distribution in the way that this probability distribution has exactly the expectation that we know it should have. So that's the general idea. Yeah, the question is now, where does this come from? So why use this kind of probability density function for the distribution of the cluster volume? And this is interesting. So where this is coming from is that in, again, the Adler book, Adler 1981, they report on page 158, this is also cited in the Fristen et al. Paper, they report that K, so essentially the cluster volume, to the power of 2 divided by D, yeah, is distributed according to an exponential distribution with some parameter. I'm actually today not completely sure about this parameter business, but the important thing for today is that this K to the power of 2D is distributed according to an exponential distribution. This has or has not, no, the historians are not quite sure about this, been derived for Gaussian random fields by a Russian mathematician called Nosko in 1969. There are 2 communications. I love this one. Does it have the thing? One is somehow in the proceedings of the mathematical conference of Novosibirsk. It's a reference in the script online. So this person, Nosko, has reported this result, which might or might not have been derived, because Adler remarks that, so Adler writes that yeah, they have strong practical relevance, this thing, also, so that you know what the cluster volume is distributed, but he also remarks that no detailed proofs are given in these Nosko communications. So somebody guessed that this might be the case. Anyway, I don't know. That is where this is coming from. Fristen et al. Then cite the result by Nosko. And then what happens, and this makes then more sense, is that this comes somewhat out of the blue, this exponential distribution of k to the power of 2d. But then, of course, we are not interested in the distribution of the cluster volume to the power of 2d, but in the distribution of the cluster volume. And then what Fristen et al. Did in 1994 was to use what is called a change of variable, which sounds a little bit harmless because it sounds like you instead of writing k, you write x or something. But what this really means, this is the English term for what the Germans call the probability density transformation theorem. So this is actually how the whole thing should work in principle, is that you know the distribution of this, and then you apply a function to this. So for example, you apply to k to d, you apply the function d, so you apply the power d divided by 2, so that you actually get k. And at the same time, while doing this, you ask yourself, okay, I know the probability density function of this thing. What is then the probability density function of this? And for this, there's there's what is called the probability density function theorem. So I basically reproduced this proof by Fristen et al., which is not documented in the paper, of course. It's just remarked that there's this is done using a change of variable argument. So I don't want to go through all the details, but just that you know what this change of variable means is that if you have a random variable x that has a probability density fx, and you have a function g that maps the values of x onto the values g of x, and by this procedure you define a new random variable y, so g of x is called y. Then the probability density function of y can be computed in the following way. It's the probability density function of x, which you know, at the location of the inverse of the function g. So you need to define a function g, and it needs to be invertible so that you, for example, like square something and take the square root. That's at least invertible, although it's not bijective. You need to invert this, and which in this case, of course, follows this logic here, and you need to divide it by the determinant, essentially, but in this case, because it's univariate, of the derivative of the function g evaluated at the inverse of the function g at the location of y. And so you need to compute also the derivative of g. This is actually where this 2d minus 1 comes from here, this, because if you have something to the power of something, then you need to subtract 1 if you compute a derivative. So then, just as a side note, this is where this comes from. You have to evaluate this at the location of the inverse. So the most important, so these things usually, if you have these univariate probability density functions and relatively nice simple differential function, like in this case to the power of something, then basically to evaluate these derivatives and the inverse function, that's not hard. But what is hard, or what I've always struggled a little bit, is keep track of what exactly at what place. But if you do that on paper, then it actually is not that hard. So this is then a way how you can evaluate the probability density function of k if you know the probability density function of k to d. So this is documented in this proof of 6.23, where the definitions are and everything, and then you actually get to this 2 beta dk and so on, this form. Yesterday when I prepared for that, the whole thing, I wasn't quite sure anymore about the beta. I think it was I think it was fairly simple to get from this beta. I think it's just an application of this the same function, but I haven't documented it, so I'm not quite sure. So don't ask me that, please. But the idea is that you just take the expected value that you know, and you do the same probability density function transformation also to that parameter. I think I should document it. At one point I realized that this is really simple, so this is why I didn't write it down. But I should document it because now I've forgotten what actually happened. But the probability density function, then falls out of this change of variable thing, or as Carl Friston calls it, a simple change of variable thing. It's actually simple, but it's if you don't know what is meant by it, then it's unclear what this means. So this is then how a probability density function for the cluster volume enters the whole RFP business. So again, this is based on a result by Nosko, reported in Novosibirsk, and maybe proven or maybe not. Actually, the other thing is, of course, I tried to look for these Nosko papers, but I only looked online, so I didn't travel to Novosibirsk or somewhere. And so if somebody wants to do a master thesis, then one could try to find these Nosko papers in some Russian archive, or maybe even here, maybe there who has it, I don't know. I just don't do paper literature search these days, because usually it's not required. So these NOSCO papers that you don't have access to, Adler says they are not proven, so nobody knows where this is actually coming from. But then, if this is there, then this transformation makes sense, and this cluster volume probability density function falls out. One other thing that is important, because we will also need it later, is if this density is there, one can of course also compute the cumulative density function. And if one has what is called an absolutely continuous random variable, so this involves things like the Radon-Nikodym theorem. But again, if you are only familiar with Gaussians, then you can also appreciate that fairly quickly. So there is a relationship between probability density function and cumulative density functions, in the sense that the probability density function is the derivative of the cumulative cumulative density function. Yeah. So one can write if something like this: the derivative of Ku is the density function of Ku. This is in mathematical probability. It's not as trivial as I presented here, but nevertheless, in kind of nice cases like probability density functions of the Gaussian, or in this case, one can use this to establish a relationship between the probability density function and the cumulative density function, and then one obtains for the cumulative density function in the current case this, which can be verified by just computing the derivative of this function, so of the big F, so of the cumulative density function, and recover the probability density function. So this is what I do in proof of 6.32. There you see that on the left-hand side in 6.33, I put the derivative of FKU, so I guessed this essentially. This is what you can do in math. You just guess something, but then you show that it's correct, or you publish it and maybe this, so this is a simple calculus thing. Of course, it uses that the derivative of the exponential is again the exponential at this location, and then you recover the density function. Yeah. And because the probability, the cumulative density function corresponds to, so let me write this up once again, because we need it all the time. So FUK is probability that KU is smaller than K. Actually, in the case of these absolutely continuous random variables, where you can do these derivatives and do integrals in the Riemann sense, this smaller than or equal to doesn't matter, because as you know, for a Riemann integral, it's the same if you integrate on the interval, on the closed interval, or on the open interval for Riemann integrals. So the smaller or equal to is the same. What we will need later is the probability that a cluster takes on a value larger than k, which is of course then 1 minus the probability that it takes on a value smaller or equal to k. This is the density function. So if we do 1 minus this density function, then we get 1 minus 1, that's 0, plus this, because we take 1 minus the whole thing, and then we get this fairly simple expression, exponential of k to the power of 2d. Yeah. So that's the probability that a cluster in the excursion set takes on a value larger or equal to k, and this again just follows from essentially the definition of the probability density function, which you can then use to evaluate the cumulative density function, and to take the complementary cumulative density function, which is just this. Yeah. Good. Questions about the distribution of the cluster volume? No. Good. So then we now have actually done the fundamental stuff, and then the next thing, because I'm clearest about it, is to discuss the number of clusters of a given volume, or more precisely of a volume larger than a constant, which we've just seen here. So. So essentially, we're now not interested in the number of clusters and independently in the expected volume of these clusters, but basically in their joint distribution, if you want. And why is this important? This is actually this is really, really important. This is why I spent a little time on it, and it's also and why I also presented before the maximal cluster volume. Why is this important? Because this is the basis for all the p-values in the SPM table. So what Carl Friston likes, and this is based on Friston 1996, and what I also like, of course, and everybody should like, is to generalize things. So of course you all know that he is very active in the free energy principle, where the fundamental idea is that everything that the brain does is variational based, and then you work out the details. And in the same spirit he has always worked, and in this 1996 paper what is discussed is an expression for all the p-values in the SPM table. So for the set level p-values, the corrected and uncorrected one, for the cluster level p-values, corrected and uncorrected, and for the peak level corrected and uncorrected p-values. And this general expression is based on the distribution of the number of clusters of a given volume, or of a volume larger than a constant. Now, if you read this paper, and I read it many times over the last 10 years, and actually only last week I finally understood what this is about, you will find that it's not clear. Or at least I found it very not clear. If you read it and you find it clear, then I don't know what's going on. But the problem is that it's not clearly discussed what the probabilistic model is that is behind this expression. So this is not communicated. But what I now try to do is infer this from the equations. And then I found, and this is what I found over the last couple of weeks, is that in one of the first equations where this thing is introduced, there's a typo, and that also doesn't make things easier. You can tell that it's a typo because in the appendix the same expression is treated again, and that looks different, and then it makes sense and one can understand what it means in the appendix, but in the expression like it's in the paper, this typo makes it really hard to understand what's going on. In any case, this distribution that we now discuss is kind of the mother distribution for all the things that follow. We will not discuss today how the specific cases that we've discussed previously follow from that. We will do that when we discuss the SPM table, but we will discuss this thing now. And to put this in a right framework, we first have to define a random variable or two or something for which we want to define the distribution. And the random variable that we use is, I will call Q, and I will denote it by subscript larger than K. And because all of the random variables that we've discussed so far have a subscript U, because they depend on the threshold of the excursion set, I will also give it this subscript U. Yeah. So don't worry about this complexity of notation. The larger than K is really important. This U is just there because it's always there, and I also wanted to have it here. So what does this random variable describe? It's should model, so it's a random variable that models something, and it models the number of clusters. So it's a number of clusters in an excursion set that have a volume larger or equal to K. Yeah. So imagine you get a realization of an excursion set, and based on some threshold U, and then let's say you have in total you have 10 clusters. Then you look at the volumes of these clusters, and you find that these volumes are 5 times you have the volume 4, and the remaining volumes are 6, 7, 8, 9, and 10. And then you ask what is the number of clusters that have a volume larger than 8 or equal to 8, and then you know that the ones with a volume of 5, they don't have a volume larger than 8 or equal to 8, and also the clusters with the volume 6 and 7 don't have a volume larger than 8, but the clusters with the volumes 8, 9, 10. So you have 3 clusters that have a volume larger or equal to 8. Of course, you can change this value K, but what this random variable represents is the number of clusters that have a volume larger than a given size. Yeah? Now, the basic result of Friston 1996 and everything behind the SPM table is that this random variable is distributed according to a Poisson distribution. So again, a Poisson distribution with parameter lambda K. So it's just the parameter of this random variable. Again, maybe it's a little bit of overkill of notation, but we just seen a Poisson distribution that has a lambda as a parameter, and this lambda and this was a different parameter because it referred to a different random variable. So this lambda refers to this random variable, and this parameter, which of course because it's a Poisson distribution, refers to the expected value or parameterizes the expected value of this random variable, is defined as the expected number of clusters times the probability that a cluster takes on a volume larger than K. Actually, that's kind of intuitive, of course, because we are talking about the number of clusters with volume larger than k, and then the expected value is the expected number of clusters times the probability that that the volume of such a cluster is larger than k. So it's kind of intuitive, although if one starts thinking about it, the assumption here is that the number of clusters and the volume is independent, and that's, from my perspective, a fairly strong assumption, because if you have a limited overall volume, then of course this cannot be independent. So if you have a cluster expectation that is almost as volume expectation that is almost as large as the search space, so most of the time you would get a cluster, the excursion set, you will get a cluster that fills out the whole excursion set, then of course the number of clusters that you can get is not independent of that. But then these independence assumptions are sometimes helpful to at least get started. And if the clusters are fairly not that large compared to the excursion set, and the numbers are usually relatively low, then this independence assumption is okay. Now the question is, nevertheless, even if we talk about this expectation that this is relatively intuitive, the question is, why should this whole thing have a Poisson distribution? And this I want to sketch now. So where does this come from? What is going on? And this can be justified as follows, which is somewhat inspired by the argumentation in the Friston 1996 one, although it doesn't make these things really explicit. So the basic motivation for this is that we assume that we have a random variable Cu, which models the number of clusters, for which we actually have a parametric form. So remember, we discussed that it's a Poisson distribution, so we know that this is Poisson distributed, although this is also based on somewhat thin ice. But we know that this is Poisson distributed, and we are now look at this new random variable that we just discussed. And what we are actually interested in is the distribution of this. Yeah, so this is what we want to derive. So we want to make a statement about the probability distribution, or let's make that even simpler. We want to make a statement about the probability, so P, that the number of clusters that have at a given defining U value have a volume larger than some value K, for example 10, and we want to make a statement about the probability that this is, for example, 3. Yeah, so like we've just discussed for our K equals 8. So we, in more general, we want to say that this is I. Now, what we can actually talk about is the joint distribution of the number of clusters. Ooh, there are U's missing in your handout. Of the number of clusters and this new random variable, because this, of course, according to the law of conditional, not the law, the definition of conditional probability, factors into the conditional distribution of larger than Ku given Cu. Yeah, this we know. And if we want to evaluate this joint distribution, then we need to define this. Why do we want to evaluate the joint distribution? Because if we marginalize the joint distribution, so if we sum this over all values that I might take, so all number of clusters that are possible, so if we consider this, if we marginalize this joint distribution over this random variable, what do we get? Think again about the table that you all filled in the winter term. If you have a joint distribution and you marginalize over one random variable, what do you get? You did that. You did it by hand. You all passed the exam. Exactly, yeah. Then you get the marginal distribution of the other one. So if we marginalize out this Cu, then we get the probability distribution P, Q, Ku. Yeah. So this is why we want to consider this joint distribution, because once we have it, then we can marginalize it and we get our distribution for this new random variable. However, if we want to do that, we have to define the probability distribution of Cu. We've done that already. We have it here, but we haven't talked about this. And this is then what is defined actually in the Friston 1996 paper, although it's not explicitly communicated like that. So the question is, what is the conditional distribution of this random variable given Cu? And of course, this is not a question for you, but this is a question of definition. The point is that this is defined as a binomial distribution. So remember that we discussed binomial last time, with parameter mu, where mu is the probability that Ku is larger than K. So remember that we also above have an expression for that. Yeah. What does that mean? That means in the case that we have J clusters, yeah, so assume that we have J clusters, so let's say 5 clusters. Yeah. These are our 5 clusters. Then there is a probability for each of these clusters to have a volume larger than K. And of course, there's also the reverse probability, that the probability of this cluster is smaller than K, which is just 1 minus Pk larger than K. And one of those is then a Bernoulli trial, like we discussed Bernoulli last time. So it's like a coin. There's a probability that this cluster has a volume larger than K, which is, let's say, depending on the value of K, it's 0.8. If K is fairly low, then it's very likely that this is larger than K, and 0.2 that it's smaller than K. And if you increase K, then of course the probability might decrease. But the point is that these J clusters all have this probability to be individually larger or smaller than K. And then the sum, or yeah, let me call it the sum of the clusters that have a volume larger than K is given by a binomial distribution, right? So in the same sense that we discussed last time, that if you have 10 trials of throwing a coin, which outcomes 1 and 0. Here the outcomes 1 and 0 are the event that the volume is larger than K, and 0 is that it's smaller than K, for example. Then if you model this as a sequence of 1s and 0s, then the question is, if the individual probability for each coin, or in this case for each cluster, is 0.5 or 0.6 to have a certain property, what is the probability of observing in the set of 5 or 10 or whatever to observe 1, 2, 3, 4, or 5 that have this probability. Yeah? So the crucial thing to understand this is actually that you're clear about the relationship between the Bernoulli distribution and the binomial distribution. If you're clear about this, then the definition of the following makes a lot of sense. So the conditional probability of this random variable Ku to be I given Cu equals J. So for example, 10 clusters, and the question is what's the probability that 3 of them have a volume larger than K. takes on this form, which is just the form of the binomial distribution. So we need the binomial coefficient, and we need our mu I 1 minus mu j minus I, where our mu is the probability of a cluster taking on a volume larger than k. Yeah. So this binomial distribution of the number of clusters having a volume larger than k as a binomial distribution makes sense if you know that the probability for an individual cluster to take on a value larger than k is this and that. Yeah. So what this allows, so if this is defined, and this is how it's defined, so this is a definition, that's the RFP or the Friston 96 definition of the conditional distribution, which is sensible and which also uses something that we already know because we discussed that. If you use this as the conditional probability distribution, then both these terms here are defined. Yeah, so we've just defined this, and this we've defined already. So this means that we can now evaluate the following: P Q larger than K U is, as we discussed earlier, is the marginalization of the joint distribution. In this case, we allow for infinitely many clusters, although it's a little bit interesting, at least. So we marginalize over J the joint distribution of these two random variables, like you did in your table in your exam, only that we, instead of computing everything by hand, we look at the formulas, but we marginalize out this one to get this distribution, and we can basically put in the respective forms. So we have the Poisson form, which I'm just writing out, and then I almost stop. So the Poisson form of the marginal distribution of Cu is this, and the binomial form of the conditional distribution is if you write out the binomial coefficient. So instead of putting the binomial coefficient, you write it out explicitly. It looks even more mathematical because you have these exclamation marks. It really looks great. And so this is just the binomial form. So that's mu to the power of I 1 minus K U P J minus I. So now I just put in, so this is, just to emphasize this again, this is the conditional distribution that we defined above. This is the binomial form if you just write it out and put the parameter in. Given Cu, and this is just the Poisson form that we discussed previously with the expectation parameter, expectation of Cu. This is the distribution of the number of clusters. Now, if you do that, and then start to do some math, or essentially simple algebraic reformulations, which you see in the proof of 6.4, where, because of course this is very long, I instead of writing ECU, I wrote A, and instead of writing PCU larger than K, I wrote B. Then if you do this, and this is exactly what is written in the appendix of the Friston 96 paper. You can, by actually just changing the running index, which doesn't matter because this whole thing runs to infinity, you can then, by realizing that you actually at one point have the series definition of the exponential function, you can simplify this whole expression and get actually to what you see in 645, which is then again a Poisson form. And then if you define, like I did here, if you define this, then you are here. Yeah, so these little details in the proof, that's a nice exercise for lonely weekends, which you all have as master students. And it's really simple. So there's just a little bit of taking things out of a sum or using the laws of exponentiation. The more tricky thing for me actually to work out where this is coming from was to understand what kind of probabilistic model is behind that. And the point is that it's this it's this joint distribution of the number of clusters and one random variable that represents the number of clusters that has a volume larger than k, and the marginal distribution of the number of clusters is defined as a Poisson distribution, and the conditional distribution of the number of clusters that have a volume larger than k is defined as a binomial distribution with the parameter of the probability of an individual cluster to have a volume larger than k. Once you know that, the rest is mechanics and fairly simple. So if you, again, at one point write a paper like Friston 96, make it easier for everyone in the field by explicitly writing what your probabilistic model is, because then it's easy to understand. And even if there are then typos, it's much easier to identify the typos than if you don't make explicit what your probabilistic model is. I'm safe. You will not watch this. So one thing that is left, which we will not do today as planned, is the maximal volume, which is fine, because the thing is, this is from the 1994 paper, the maximal volume, and I just realized recently that this actually rests on the same framework. You can motivate this differently, but you can also motivate like this, so I want to get into this framework. What is important about this? You might think, oh, there's so many equations, it's all annoying, I don't understand what this P with the two thing means and so on. Yes, that's fine, and it's all annoying, but this is, if you go into the SPM code and you look how the values in the table are evaluated, what is happening is that this thing is computed, and essentially k, so your cluster size, your cluster defining threshold, is put into a function that is called SPM PDF plus or something, which is this Poisson function, and what this function returns is what is printed into the SPM table. So you cannot understand what the SPM table wants to tell you if you are not aware of the fact that it's based on this Poisson distribution. And once you know that, of course, you ask yourself, why Poisson distribution? And the answer is, basically what is in your script 6.24. Yeah, so might appear annoying and detailed and tedious, but is what everybody bases all their theories about how the brain works and what consciousness is and what is amygdala doing and so on. Actually, I thought about SPM, I always thought about SPM and wondered how many people do really use it. And last week I found a paper that did a survey. It's not a big cohort, but it's at least around 150 people in the US. And US is not really SPM hotspot. Europe is the SPM hotspot, but in the US, of these roughly 150 people, the survey was on data sharing, but they also asked, what software do you use? And 70% in the US said they use SPM. So that's actually real numbers to know how important that is. And don't forget, FSL implements the same thing. So everybody who responded to FSL does the same thing. Although I'm not quite sure whether they also use this Poisson thing, because I don't think they have the set level. Good, so I stop here. Any questions? Yeah.
What can we use in the US?
No, like I said, so I always thought that the US is a little bit more AFNI, or maybe the Vision Labs, actually maybe Brain Voyager or FSL or so, but it turns out that according to the survey, SPM was also the main thing used. And in Europe, SPM is definitely the main thing used. That's what I always felt, except for Oxford, of course, which is an FSL. But again, the random field theory p-value correction framework is by and large the same in SPM and FSL. Other questions? No. Good, then let's stop here and continue in a short time in the other room.